Okay, fourth and last paper for this session is going to be UniGRe-3D, Unified Geometric Reconstruction for Multi-Category 3D Anomaly Detection. And the presenter is Yuting.
Hello everyone, today I will present the paper UniGRe-3D, Unified Geometric Reconstruction for Multi-Category 3D Anomaly Detection. This work mainly focusing on 3D point cloud anomaly detection in industry scenarios. The goal is to use unified models to perform the anomalies detection and anomaly localization across multi-product categories. First, I would like to introduce the research background and motivation. In the industry inspection, products defects often appears as local geometric changes, such as cracks, dents, holes, and protrusions. Compared with the traditional 2D images, the 3D point clouds can directly describe the spatial structures of object surfaces. Therefore, they are less affected by lighting, texture, and background interference, and they are more suitable for detecting geometric anomalies. The core objective of this task includes two aspects. The first is to determine whether a given sample is anomalous. The second is to further localize anomaly points or anomaly regions. However, many existing 3D anomalies detection methods usually require training a separate model for each product categories. In multi-category industry product lines, this leads to repeated training, increased model strategy, and higher maintenance costs. Therefore, the main motivation of this paper is to move from category-specific models to unified multi-category models, using one shared model to detect and localize anomaly in point clouds from different categories. However, unified multi-category models also faces clear challenges. Different products categories have the large geometric variations, where anomalous regions are often very local and subtle. Therefore, the model needs to learn shared normal geometric patterns across different categories, while still remaining sensitive to fine-grained local anomalies. To address these challenges, this paper proposes UniGRe-3D, which improves the unified multi-category 3D anomaly detection through the local global geometric encoding and position-guided hierarchy reconstruction. Next, I will briefly introduce existing method. Current 3D point cloud anomalies detection methods can generally be divided into two categories. The first category is feature embedding method, and the second category is the reconstruction-based method. Feature embedding method usually extract features from normal samples and build a feature memory bank. During testing, anomalies are detected by measuring the distance between the test sample's features and the normal features. These methods usually achieve strong detection performance, but they rarely rely on the memory bank, which bring additional strategy and matching costs. Reconstruction-based methods usually train an encoder-decoder network using only normal samples, so that the model can learn the geometric distribution of normal data. During testing, if a certain region cannot be well reconstructed, it may indicate the presence of the anomaly. Reconstruction-based methods are more suitable for unified modeling, but their performance highly depends on the reconstruction quality. If normal regions are not reconstructed well, false positives may occur. If anomalous regions are also reconstructed, false negatives may occur. This slide shows the overall framework of the proposed method. First, the model uses FPS, which stands for Far East Point Samples, to sample point cloud certain centers, and then use KNA to construct local point groups. After that, a frozen point MAE is used to extract point cloud token features. In the feature encoding stage, the model uses the LJE model for local global features enhancement, including multi-scale features, fusion, and the LGFA model. In the decoding stage, this model uses the HRD model for hierarchy reconstruction, including position guidance and the HPRM model. Finally, anomaly scores are computed based on the difference between the original features and the reconstructed features. In other words, this paper does not directly detect anomalies in the original point cloud space. Instead, it measures the deviation between normal patterns and the test samples in the feature reconstruction space. Now I will introduce the first core model, LGFA, which stands for Local Global Fusion Attention. The core of this model is to model both local contextual information and global channel response after multi-scale feature fusion. LGFA mainly contains two component branch. The first one is a local branch, which uses one-dimension depth-wise convolution to capture local dependence among tokens. This helps the model focus on local geometric changes, such as crack stains or local protrusions. The second one is the local branch, which uses the average pooling and an attention MLP to model channel-level global response. This allows the model to determine whether a local geometric changes is truly anomalous by considering the global context. Then the local and the global features are adaptively fused and injected into the output features through a residual connection. The key point is that LGFA jointly enhances the local geometric details and the global semantic responses, improving the cross-category anomaly discrimination. Next, I will introduce the second core model, HPRM, which stands for Hierarchy Progressively Reconstruction Models. The key idea of this model is to use the position guidance to progressively recover normal geometric patterns in the feature space. HPRM contains the three reconstruction level, coarse level, medium level, and the fine level reconstruction. Coarse level reconstruction mainly focuses on the overall structure. Medium level reconstruction future supplements local region information. Fine level reconstruction is used to recover more subtle geometric features. Each reconstruction branch consists of two linear layers, one nonlinear activation function and one dropped layer. The main difference lies in the activation function used at each level. Finally, the model integrates the reconstruction results from different levels through diamantic fusion and a gating mechanism. It should be noted that HPRM does not simply reconstruct the point cloud 3 times. Instead, it progressively recovers the normal patterns in the future space. The advantage of this design is that the normal region can be more accurately reconstructed, while anomalous regions which do not conform to the normal geometric distribution tends to produce larger reconstruction error. This is helpful for anomalous localization. Next, I will present experimental results. On the anomaly-shifted net dataset, the proposed method is compared with several advanced category-specific methods and unified modeling methods. The result shows that as a unified modeling method, UniGRe-3D achieves the best overall performance in terms of the objective ARC with an average score of 91. This is a significantly higher than the existing unified method, MC3D-AD, which achieves 84.2%, and also higher than the strong category-specific method, PO3AD, which achieves 83.9%. This results indicates that the UniGRe-3D can still achieve strong overall detection performance without training a separate model for each category. It demonstrates the effectiveness of unified multi-category modeling. Now I will introduce the visualization results and ablation studies. The visualization results are presented on the anomaly-shaped net dataset. In the visualization, the red region indicates the anomalous area predicted by the model. The blue boxes indicate the ground truth anomalous regions, while the red box highlights the region where MC3D-AD produces missed detection or false positive response. From the quality results, we can see that compared with MC3D-AD, the anomalous localization results of UniGRe-3D are generally closer to the ground truth. It can also reduce some false positive responses. This suggests that the proposed method performs well not only in objective level anomaly detection, but also in point level anomaly localization. The ablation study further verifies the effectiveness of two core models. When only LGFA is used, the model achieves an objective ARC of 0.907 and a practical ROC of 0.8. When only HPRM is used, the model achieves an 0.890 and a practical ARC of 0.791. When LGFA and HPRM are used together, the model achieves the best objective level results with an OARC of 0.911. This shows that LGFA and HPRM are complementary. LGFA mainly enhances anomalous sensitive feature representation, while HPRM further improves the reconstruction ability for normal pattern. Finally, I will summarize the application value and the limitation of this work. In terms of the application value, UniGRe-3D uses a single model to perform multi-category 3D point cloud anomaly detection. This reduces the cost of the repeated training model strategy and later maintains for different categories. Therefore, it is more suitable for automated quality inspection in multi-category industrial production lines. For real industrial scenarios, this unified modeling strategy can improve deployment efficiency and help reduce the complexity of system maintenance. In terms of limitation, although the model achieves good performance on the synthetic data size, point cloud noise and scanning artifactors in real industry scanning scenarios may still affect the detection performance of unified reconstruction-based models. Therefore, future research should further improve the robustness of the model against the real scanning noise and complexity shape variants. That is the main content of my presentation. Thank you for your attention. I should clarify that I'm not directly involved in the original research, so I just present this work on behalf of the author today. For the technical details, I would recommend contact the author directly. Thank you.
Questions? Okay, so since we're also going for lunch, I'd like to thank the speakers of the session again, and bon appetit.